we'll talk about the numerical differentiation, and this is the final major part of this semester, and the numerical methods for ODEs, right? ODEs, ordinary differential equation. So these things are motivated by we have to solve numerically ODEs. Okay. Before that, let me try just list a few things for you of the ODE concept. Some simple ODE concepts, all right, which you may have seen from the ODE class. So what ODEs? ODEs are in general the following form. We are going to have y prime is equal to f of ty, right? And you are given an initial condition y is function of t, right? So we meant that we need to find y of t such that, right, y is function of t. Again, t is just a variable. It can be x, can be another letter, right? But we think of this as time. Okay, it's a dynamic system that's changing with time. Okay, y can be the position of something, of a ball, right? For example, we have y prime is equal to y, let's say, right? And y at 0 is equal to 1. Or maybe we have y prime is equal to 3t, and y of 0 is equal to 10. Okay? And if you're having difficulty solving this kind of ODEs, you should think hard, all right? I mean, the second guy is easy because this means y prime is 3t. That means you just integrate, right? And the fact that we're integrating will be the key for us to design the ODE solvers, which I will remind you many times, all right? All the schemes that we'll be talking about is resulting from that, hey, we have y prime is something, how do we solve for y? We integrate. Okay, if you have that map, that's a map that guides us to design the schemes, then you will be okay. Okay, so this is what, 3t squared over 2, right? Plus c, right? Plus c. You have the initial condition which helps you to evaluate that c, right? When t is 0, you should get 10. Y of 0 is 10, means that c is equal to 10. So the solution, yt, this guy is 3t squared over 2 plus 10. Right? Right. So the first guy, y prime is equal to y. Theoretically, you cannot just integrate y because you don't know y, right? You don't know y. What's better for numerically is that numerically, when again, as I just said, all the schemes are from that you're integrating the right-hand side. Numerically, you actually can. We're going to talk about it, right? So there's advantage of doing things numerically. In this case, what do? We have, anybody knows the solution to this guy? Huh? This is, yeah, I will not tell her. So the yt is e to the t, and you don't add c, you multiply c in this case. Because c times e to the t, you take the derivative, you get itself. And then based on the fact that y0 is equal to 1, you get your c is equal to, you plug in 0, you get 1, so c is 1. So the solution is that this is e to the t. I haven't explained how to solve this ODE. That's your homework, right? I'm not going to do that here. What I remind you is that you divide both sides by y. You get a y prime over y. And write this y prime as dy dt. So you're going to get dy over y is equal to dt. And then integrate. Okay. So this is called the initial value problem. Initial value problem, right? IVP. And in 362, we'll talk about the boundary value problem. That's a BVP. And another way to call this is a so-called Cauchy problem. The initial value problem. Okay. And I'm sure you heard about from ODE classes what is autonomous. Autonomous. All right, autonomous. Autonomous means that this right-hand side, FTY, right? FTY. This FTY in principle can be any function of y and t. If that FTY is actually just some function of y, g of y, then it's called autonomous. There's no t. I mean, really in quotation mark, right? There is t. There is a t dependence. What is the t dependence? There's no explicit t dependence. It's not like, here you see a t, right? Here is autonomous. Y prime equal to y is autonomous. There's no t. There's no t explicitly. But in fact, there's a t dependence because y is dependent on t, right? So it's implicitly dependent on t through y. I.e., so if i.e. The t dependence is only through y, right? Like the one we just talked about, e.g. Y prime is equal to y, or maybe set any constant times y, 3y, right? That's an autonomous system. Okay. So I'm going to mention two more things because those are things that will be related to what we do later, right? Here is not really numerical methods, but just some ODE stuff. The second guy is so-called Lipschitz continuous. Lipschitz continuous. Okay. What we need here is that this is some very basic ODE theory, which is if you have that means we have existence and a uniqueness of solution to ODE. So you give me ODE, how can I make sure there's a solution, right? What do we mean by Lipschitz continuous is the following. So if the only thing you need to check is that if I do FTY1 minus F, my right hand side, right, Y2, is this guy less than or equal to some constant times Y1 minus Y2? Okay. Y1 minus Y2. Lipschitz continuity is between continuity and continuous differentiable. If all right, so again, this is stronger than continuity, and in general we have the continuously differentiable. This would means the Lipschitz continuous, which Lipschitz continuous is stronger than continuous. If the function is Lipschitz continuous, then it is continuous. So this sort of between. So that's like C0, right? There's a notation for this is C0, that's C1. Lipschitz is between C0 and C1. C1 means the first one is for first. The first derivative is C is for continuous, right? This means the first derivative is continuous. This means the function itself, zero's derivative, is continuous. C0, C1. Lipschitz is between 0 and C1. So if you see, for example, if our ft(y) is 3y squared plus 4t, then we know this guy. So we're talking about y prime is equal to 3y squared plus 4t, right? Does this have a solution? The answer is yes, because this guy is already, the right-hand side, the f is already continuously differentiable with, because if you take the derivative, you get 6y. 6y is continuous. Okay, so you take the derivative. So this ft of y is c1 with respect to y. The reason is you take the derivative, you get 6y is continuous. So there's a solution that satisfies the condition. Is C1 or is Lipschitz? We don't really need this for. I mean, that's just like to the sanity check, right? If you try to design a scheme to solve for a solution, the ODE better has a solution. Otherwise, what are we solving for? Right? That's why we're doing it here. But for our schemes, for this class, we're not going to do anything related with this. Okay, does that make sense? If we try to solve for a solution, we better make sure the solution exists, right? But the next concept we are indeed doing quite a bit later, with something called it is a stability concept. The stability concept is probably a bit confusing to start with, but I will throw this out here. We'll come back often later, okay? There is an important concept in mind. So what this means is that, on paper, we're solving the y prime is equal to ft(y), y0 is equal to some initial condition, y sub 0. Y sub 0 is given, like what we did, the 10, 1 above, right? The initial condition. So that's what we do on paper. As we were explaining from time to time. Now we're doing things on computer by numeric schemes. It's not really, nothing is really exact. Or at least very, very few things are exactly representable on computers. So on computer versus VS, on computer we're talking about, okay, we're solving something slightly different because of the round of error for one thing. Say we're solving z, right? Z prime is equal to ftz plus some delta t. Delta is small. And z when t 0, this is equal to, it's not really y0, but also some delta. And delta is small. It's small. The round of error or some other, if this is after previous scheme, is error from the previous scheme. If you solve for the right-hand side, right, and then you get an ODE. I'm not going to write down the exact definition. There will be an epsilon delta kind of language. Maybe I should. And then give you the colloquial interpretation of this, right? So what does this mean? What is the stability concept is that there exists epsilon, right? Epsilon is small, epsilon larger than 0 is small enough, and a c, right, a constant c is larger than 0, such that if my delta t, right, the perturbation, the round error, the perturbation is small enough, if that's less than epsilon, and my delta t includes the delta of 0 already, right, then y minus z is less than c times epsilon. Then we call the system is stable. If the system is stable, right? So what this means is that if you have small perturbation in data, right? In data, the initial condition is your data. You have an initial condition. The right hand side of your data. If you perturb it, you shake it a little bit, right? Then the solution is also shaken just a little bit, because by little bit I mean absolutely small. The solution is also away from your exact solution. Y by only c times that is absolutely tiny. C is or c times absolute is also tiny. C absolute go to 0. C times absolute go to 0. So in plain language, this means that small perturbation. Oh no. Small perturbation in data leads to small perturbation in solution. Right, solution. One example you can think of is that if you what's that? If you have a ball, right? You have a ball. You put it on in a valley, okay, in an x squared curve, right? The lowest point of the x squared curve. You put it in the bottom. If you shake it a little bit, what do you think? Would it fly out of the ball? No, right? It will go back to the lowest point of the ball, right? A cup. On the other hand, if you have a bell, you put it on top of the bell. If you shake a little bit, it will fall off the bell, right? So the first one is stable, the second one is not stable. This kind of things happens everywhere in the numerical schemes. For a stable scheme, later on we're going to talk about, okay, for OD solver, OD scheme, which ones are stable, which are not stable. Those are less intuitive than the ball, right? But it means the same thing. It means if you shake a little bit, it will go back to the original. It is close enough to the original location. But in that case, you shake a little bit, if it's not stable, then you don't have this. Okay. So those are only the three things that I want to mention for the ODE concept. All right. Well, we're going to start talking about the numerical stuff. The numerical stuff. Okay. So before we move on to ODE, we'll talk about the first part, which is the numerical differentiation, right? Maybe just simple numerical differentiations. In particular, we'll be talking about the so-called divided difference. Divided difference, all right? We're going just to do very few of them because we will move on to ODE. And at the beginning of 362, you know, for those who would stay, we'll do a whole lot of these. So here y, right? Y. If we stay with y, right? Y. We're going to use y to denote the exact solution. Okay, for this part. And if we have approximation, which is what we're having, is that we're going to denote by u to be the approximation. All right. So we have a function y. Okay. Here's t. Here's y of t. Right. Y of t. Y of t. And we are at some time, right? T n, or some time Tn. I'm using the horizontal axis to denote t. Okay, and y is this function of t. You know, if this is confusing, maybe we should just change it to x, I guess. Is everybody okay with using this? Or you just have to use x? That's okay, right? That's okay. Just t. Okay, t. The derivative. So the key point here is how can we approximate the derivative at t. The goal is that we want to approximate y prime at t. Because again, to solve for the ODE, we have the y prime, right? Y prime. Y prime. Okay. And we do things in a discrete manner, which means that we're going to have the t to tn plus 1, which is you take one step forward, okay, and tn minus 1. For example, right? For example, how to get those t's? For example, if you want to solve the ODE between 0 and 1, this is like was the way we do the integration. You cut the interval from 0 to 1 into n, capital N pieces. Then I'm going to get my t0, t1, t2, so on and so forth in the very end, tn. So the step size is h, or in this case, just let's say delta t. My delta t is the step size along the t direction, is then my 1 divided by n, right? So my tn is equal to what? That's actually a good question. I remember somebody, many students were struggling with this a lot. Even though if you think about it, it's so trivial, but the first time, yes. So in general, it's t0 plus n delta t. If your t0 is not 0, in our particular case, it happens to be just n times delta t. Okay. At time level n, you have taken n steps. That's all. At time level, you take n steps from the initial step. So the divided difference, which I'm pretty sure you've seen it in calculus. There are three kinds. One, we're going to use d for differentiation, right? D plus y, right? Which is to say I'm going to approximate y prime at tn, right? The key is at tn. If I do y at tn plus 1 by y at tn plus 1 minus y at tn, I should divide by what? Yeah, the slope, right? Tn plus 1 minus Tn, which is something better than that. Tn plus 1 minus Tn is delta t, right? Delta t. N plus 1 delta t minus n delta t. So yeah, we're using this slope to approximate the tangent line, right? Okay, so you use the guy on your after you with the plus sign. So similarly, if you use the guy on the left, d minus y, which is we're going to do y of Tm minus y at Tm minus 1 divided by delta t as well to approximate y prime at Tn. You go backward. This is the backward. Over there is forward. Okay, forward. And we also have, let's just introduce them. We're going to analyze it on Thursday. So if we do y Tn plus 1 minus y at Tn minus 1, in that case, what should I divide by? Yeah? Yeah. 2 delta t, exactly. Right? This is d0. This is centered, which is also approximating y prime at Tn, right? Tn.